In this video, we'll be going through all these questions and trying to solve each of these. The first question is explain the construction, working and characteristics of photodiode. So we'll be writing the first thing, which is what is photodiode. It's a device to convert light energy into electric current, and then it's operated under reverse bias condition that we'll be mentioning. And then the construction part. See, in construction part you have the p type and n type, and you have the cathode and anode, and these two are used for anti-reflective properties. Then the light comes from the top, from the p type, and the working principle is as follows. The electrons are present in valence band, and when light comes it gets excited to conduction band, okay, and they start conducting current. In VI characteristics, you have this reverse bias voltage here and the current here, and since it's due to minority charge carriers, the current is very low. It's in microampere, and after a certain amount of time the current remains constant, okay. No matter how much the reverse bias voltage is increased, the current does not increase much, okay. So that's the VI characteristics of photodiode. In the next question, they have asked, with hysteresis characteristics, explain the working of Schmitt trigger, okay. For inverting circuit they have asked. So firstly we will be writing what's a Schmitt trigger. It's a device which outputs the waveform based on UTP and LTP, okay. So we'll be looking what is UTP and LTP. So there are two types, inverting and non-inverting. This is the input waveform and this is the output waveform, okay. The input goes high and low, okay, and we have set the UTP and LTP here. So what happens is, when this UTP, see this is the UTP, right, when this input crosses UTP at this point, what happens, this output will become low, okay. So when again it comes here and crosses this LTP, it goes below LTP, then the output will become high here, okay. Since this is an inverting Schmitt trigger, when the output is when the input is high, it goes above UTP, the output will be low, okay, and the reverse for LTP. And then we have to write the formula of UTP and LTP, and then this is the hysteresis curve, okay. See here, this is the output voltage and this is the input voltage, okay. Now we are applying the input voltage and it crosses UTP and LTP, okay. So in case it crosses UTP, see here the input voltage, if it crosses UTP, see here this is the input voltage, right. So if it crosses UTP, what happens, the output will become low. See here the output becomes low here, see output becomes low here. So that's what we are doing in this diagram here. When it crosses UTP, the output, see this is the output, it becomes low here. Similarly, when it goes below LTP, the output should become high, okay. So output is becoming high here. Coming to the next question, they have asked us to with a neat circuit diagram and mathematical analysis, explain the voltage divider bias circuit, okay. So for we have to make a diagram and write the equations for it. So this is the circuit diagram, okay. Start from here, this is VCC, and the current is divided into two sections. First one is for RC and second is for R1. When this current flows here, it further gets divided into IB and I2, okay. Applying KVL to the loop VCC, R1 and R2 means, first we are considering this one, we are applying KVL to this part. Now while applying KVL, we will get this equation, VCC minus I1 R1 minus I2 R2, and then shifting it, we will get VCC. Now see, observe here, I1 current is coming here, it's getting divided into IB plus I2, but IB current is very low, so I1 is approximately equal to R2, right. So that's what we are mentioning here. I2 is very much greater than IB, so I1 is approximately equal to I2. We will substitute the value of I1 as I2. By this equation we can find I2, okay. Similarly, we will find the VC value by considering this one, okay, applying KVL to this part, okay. We will be getting VC, then finally we will have to apply the KVL for this lower part. When we apply the KVL for this part, we will be getting the equation for IC, okay. See, to recap, first apply KVL to this part, then this part, then this lower part, okay. Then finally we have to write these two equations which is of IC and VCE. Okay, for the Q point, see what's a Q point? Q point means the value of IC and VCE. Okay, this is the Q point. So we'll write both of these equations. In the next question, we have to explain the working of R2R ladder. Okay, we'll start by making this circuit diagram. In this, first you have to make this one. Okay, and in between make these resistances, and then observe here, this is connected with S or ground. Okay, if it's connected with this S1, if it's connected with the S input, it will go to the negative op amp, and if it's connected with the ground, it will go to the positive terminal of the op amp. Okay, so this is the op amp here, and this is the circuit diagram. And see this is the binary bits B1, B2, B3 till Bn. Okay, so this will be connected either to the ground or to the inverting terminal of op amp. Okay, then after that some theory part is there, and formula. Okay, finally write this formula of V naught. Coming to the next question, we have to explain the successive approximation A to D converter. This is an A to D converter. Okay, so analog to digital, we'll give the input as analog and we'll get the output as digital signal. So we have two parts here. In first one, we what we'll do is we'll initialize the SAR, this input. See here, we'll initialize each of this as 1 0 0 0. Okay, this is the first part. For all of the questions, you will initialize as 1 0 0 0. Then after doing that, you have to compare this. See, that's the procedure. First one, when you initialize it as 1 0 0 0, it will produce an output voltage of 8 volt. Okay, see here, there is the output from here. This is V out. Okay, and if you put the values as 1 0 0 0, the DAC will give the output as 8 volts, because this is the binary equivalent of 8, right? So you will get the output here as 8 volts. Now if you provide this input voltage here, that should be converted into the digital output, and this input voltage here, for example, if you provide 11.6 volt here, and that will be compared with 8 volt first. Okay, so what happens is, first you will be comparing this 11.6 volt and 8 volts here. If this V in is greater than this VDAC, what happens is this 1 0 0 will become 1 1 0 0. Okay, in case if it's greater. If it's not greater, what will happen? This 1 will be shifted one position to the right, so it will be 0 1 0 0. Okay, this is the possible paths which can be followed according to the V in value. Okay, so if it's greater, it will go in this path, then again it will be compared. If it's greater or smaller, then it will go in the subsequent paths. Okay, so after 4 iterations you will get the final answer here. That's the decimal equivalent of, that's the binary equivalent of the V in which you apply here. Okay, analog signal got converted into the digital signal. In the next question, we have to show how IC555 timer can be used as an astable multivibrator. And this is the circuit diagram for astable multivibrator using IC555 timer. Okay, so here you have the main components, op amp and SR flip flop, and this is the input, and here you will get the output. Okay, so let's see one by one. You have two pins here. Okay, positive and negative pin, and this is the capacitor which has the initial charge as 0, and the output is also low initially. Then what happens is, see this, the output of the op amp, see here, if it's negative, if negative is more, output will be low here. If the output is if the positive is high, then the output will be high. Okay, initially when the charge is 0 here. Okay, so here also you will have 0 at the negative input, and the positive input will be a bit higher, 1 by 3 VCC, so the output will be high here. Okay, so if output is high, R means reset. Okay, so if reset is high, Q will be 0, so the output will be low. So when Q is 0, what will happen? When Q is 0, it will not go to the transistor, this will not discharge anything. That means what all the VCC is coming from here, that will go and store in the capacitor. Okay, so then capacitor will start charging. So when the capacitor's charge increases, okay, that time at pin negative and pin positive it increases. At that time when it crosses 1 by 3 VCC, at this point when it crosses 1 by 3 VCC, this negative will become more. See here, this negative will become more. When this negative will become more, and similarly this positive will become more here because of this charging of the capacitor, this positive will become more. So this S will become more here, and it will Q will become high. When Q becomes high, the output becomes high here, and the transistor will get on here. Okay, so when transistor gets on, this will start discharging all the charges. Okay, and when capacitor goes below 1 by 3 VCC, again the same thing happens. The output will become low here, discharge stops, and again it starts charging the capacitor. So in that way you will get a square waveform which is alternating high and low. Okay, in the next question we have been asked to find the minimum SOP and minimum post expressions for the following functions. Okay, so the function which we have been given is this one, and you have to find the SOP and post expression. So let's see how to do it. First step, we'll write the function which is given here. These are the min terms, and the don't cares we will write here. Then after that we'll make this table. Okay, and in this table the corresponding min terms will be marked as high, and the don't cares will be marked as X here. Okay, and after doing this we'll make the K map. Okay, so if you don't know how to make the K map, I have made that video in ADE module 2 and 3. I have explained in detail how to make the K map, and after making this K map you have to make this equation. Okay, similarly you have to find post expression also, but there is a difference in post expression. What you will do, see here, don't case you will write the same. Okay, see here, don't case you will write the same in post also, and the remaining numbers will be written in this post expression. Okay, this is known as max terms. Which are these numbers? These numbers are those which are not present here. Okay, except the min terms, except the don't case, this will be the same there also, but the remaining numbers will be written here. Okay, so after writing that, another difference which is in post is you will be marking zeros. The numbers which you have written here, those numbers will be marked as zeros, and you will be making the pairs, and after making the pairs you will write the equation here. Okay, and here it is actually d plus b plus d. Okay, so in that way you can get many equations according to how pair you are making. Next question, we have been asked to write the disadvantages of K map and how they are overcome in QM method, and finally simplify the function which they have given. Okay, so the disadvantage of K map is that it cannot be used for larger number of variables. Okay, while this can be overcome in QM method, because the procedure which we follow in QM method can be implemented in software also. Okay, so large number of variables can be solved using QM method in a much simpler form. So in that, first you will make 3 stages, and the numbers which they have given, we will be writing those binary equivalents in the first column. If no ones are there, that will be considered as a single group, and the numbers which have single ones will be considered here, and similarly for 2 ones and 3 ones, those will be considered. And after writing that, the next stage what we have to write, see here, 0 0 0 0, this will be compared with this one. Okay, so when we compare this, the first 3 bits of both of these are same, only the change is happening at the last bit. So we'll write 0 0 0 and a dash here, and inside the bracket we'll write which 2 numbers were matched, and after matching these 2 numbers, if they match here, you will make a tick mark here. Okay, you will make a tick mark here, then you will compare this one with this one, then you will get the first 2 bits are same and the last bit is also same, only the second last bit is getting changed, right? So you will write 0 0 dash 0, in bracket you will write 0 and 2, then you will tick mark this also. Similarly you will compare this with all of these, and you will be writing this here and making this as a single group. Then in the next group what you will do, you will compare each of these with all of this. Okay, then after doing that, you will make this, you will note down what are the matched pairs, and for the last one also you'll do the same thing. Okay, after doing that you'll move on to the stage 3. In stage 3 you will compare each of this with the next group. Okay, so for example, see here, see, first you will compare this number 0 0 0 and dash. So you will find this number which is ending with dash. Okay, that number you will compare. Okay, see, it's 100 dash, right, and this is 000 and dash. So the change is happening at the first bit, rest all is same. So what you will write here is the changes happened at the first bit, so you'll write a dash there, and the rest remaining is same, and you'll write those two numbers which were matched, 01 and 89. So you'll write here 0189. Similarly you will do for all others, and which are getting matched, tick mark it, and that's it, you will get the stage 3. Okay, further no more numbers are similar here in these two groups, so there will be no stage 4. Then after doing that, the remaining numbers all will be taken here for the selection of prime implicants, and those numbers will be taken from this group and this group which have no tick mark. Okay, which were not matched. So in this case this number is not matched here, this one and this one, so these 3 will be taken, and these 4 numbers, okay, these 3 numbers will be taken. Since these both are same, we'll take it a single time. Then in the next step, it's about selection of prime implicants. See how we will get these numbers here, a dash c dash d. This is for the a. Okay, see, a was this one. Now this is according to this name here, a b c d. See here, with b it is a dash, so we will not consider b, and a is 0, so it will be a dash, and with c it is 0, so it will be c dash, and with d it is 1, so it will be d. So we will be taking this one, a dash c dash d. Okay, similarly we will do for all others also. We will write these terms, and for a dash c dash d you have 1 comma 5 from here. See, this is 1 comma 5, right, so that you will write here, and write all these terms in the function which they are given. Okay, these all numbers. After writing that, you have to make those numbers as x here which is present in the min term. See, this is 1 comma 5, right, so you will put a cross mark at 1 and 5. Okay, similarly for all others also you will do, and after doing that your next task is to find those columns which has just a single x. Okay, this has 2x, this also has 2, and the columns which has 1x is this one and this one. Okay, see, in this 14th and 9th column you have just a single x, so circle it. Okay, after circling, make a group of as many x as you can. So after making a group, what you are supposed to do, you have to note down which numbers are left here. See, after making a group, all the minterms should be covered by x. Okay, see here, 0 is covered by this one, 1 is covered by this one, 2 is covered by this one, but 5 is left. See, none of these both groups don't have x here, so 5 is left. Similarly 7 is also left. Okay, and rest all terms are covered by these two groups. Okay, so you will try to find a group which has both of these terms. So the group is this one, 5 comma 7. So these 3 terms are the essential prime implicants. In the final answer you will tick mark these 3 terms. Okay, and then write the final answer as the sum of these 3 terms. Okay, in the next question we have been asked to write about map entered variable method, and by using this method we have to simplify the following equation. See, in map entered variables we can use this method to simplify the function with more than 4 or 5 variables, and it's an extension of the techniques used in K-map method. Okay, after writing that we will simplify the function which they are given. Okay, first make this truth table. Okay, after making the truth table, for these terms mark as 1, and the don't case will be marked as x. Okay, and after doing that you have to make this map entered variable table. Okay, in this table you will mark see, a, b, c and d. Okay, according to the truth table you will mark what is the value of 0 0 0 0, for y. Okay, similarly for 0 0 0 1. Okay, similarly you will mark for all other values, and after marking you have to write down this y value. How you will write? See here, for both of these inputs it's 0, right? So you will write here as 0. If it's 1 for both, you will write 1. The change comes here if it is x. Okay, both of these are x, you will write as x. Okay, then see here it's changing here, it's 0 and 1. So according to this d, if when d is 0, this is also 0, when d is 1, this is 1. So the output will be d. So you will write here as d, and this is also the same, you will write as d. Now this is a bit harder one, how to convert this truth table into the equation. So please listen carefully. Okay, so see here, first we will make the K map for a, b, c. For a, b, c values we will fill this according to the above values which you got for y here. Okay, these values will be filled in this table. Okay, after filling these values, our first step is to make all the variables as 0. Now the variable is only d here, so wherever d is there, make it as 0. Okay, see, I have made here as 0, and then find the SOP. Okay, so I'll make this one pair here and this one pair here. After finding the SOP, write the equation here. Okay, that's your first step. In the second step, what you have to do, make the d's as 1. So d's were here, make it as 1, and 1's as x. So the previous ones were here and here, right? See here, the previous one was here and here, so make it as x, and then find the SOP expression. Make this as one pair and this as one pair. So you will get the equation here, and then what you are supposed to do is multiply this equation with d. Okay, so this equation will be there, multiply with d, you will get this final equation here. Okay, then your last step is to see, this is the equation which you have to add with this one. Okay, in the next question we have to draw a flow chart to explain the procedure of determining the minimum sum of product using K map. So determining the SOP using K map is a simple 4-step process. In the first one you will make the truth table and write the values, and then you will make the K map here and fill in the values according to what terms they have given, and then make the pairs and quad or octet which you get, and then write the equation here and simplify it using Boolean laws. Okay, the next question is to use the QM method to simplify the function which they have given. Okay, this is the same thing which I had discussed previously in the previous question. So first we will write the function which they have given, but in this question they have given the don't care values also. Okay, so let's see how to approach this question. First we will write those numbers with single ones, and then with double ones, and then with 3 ones and 4 ones. Okay, after writing this we have to compare each number with the next group. Okay, and we will note down these values here. The matched pair will be ticked, the same thing, everything. Okay, the change comes here when you write the prime implicant chart. You will write all these numbers, all these terms which were not tick marked, and then see here, you will not mention the don't cares here. Okay, see, the don't cares were 1, 10 and 15, right? You will be using 1, 10 and 15 in this part for simplifying. See here, 15 is used, 10 is used, and 1 is also used, but while writing the prime implicant chart, for don't cares it will not be used here. And then you will do the same thing, find the column which has single x, and then make the pairs and try to cover all the min terms. Okay, and that's your final answer. The next question they have asked is with an example explain the Petrik's method. Now Petrik's method is similar to QM method, just change will be there at the last term. See here, in Petrik's method also you will do the same thing, the function which they have given, make these stages as QM method and write these values, and after that make this prime implicant chart. Only the change comes here is after writing all these values you will mention it as P1 to P6. Okay, then you will write the values for each of these min terms. So for 0 it will be P1 plus P2, for 0 it is x here for P1 and x here for P2. So you will write 0 as P1 plus P2. Similarly for all others you will write this one, and then you will multiply each of this term. Okay, then after that you will have to apply some laws to simplify the equation, and it's not that hard, because see what law you will apply here. First you have P1 plus P2. Okay, search another P1 here, you will have P1 plus P3 here. So according to this law, A plus B into A plus C is equal to A plus BC. So P1 plus P2 P3 you can write. Similarly you can find other two terms also, and then you can expand this, and after that you have all these solutions. These are all the possible solutions, each of this term, and you can select any of these terms and write the final answer here. Okay, so you will be writing this P6 P2 P3. Okay, now how you will get this? See, P6 we have taken here as AB. Okay, see here P6 we have taken as AB, and P3 we have taken as B dash C dash. Okay, so we will be writing P6 here as AB, and P2 as A dash C dash, P3 as B dash C. Okay, so in that way we will be mentioning the final equation. In the next question we have been asked to write what are hazards in digital circuits and explain the different types of hazards. Okay, so hazards is nothing but the unexpected outputs which we get because of gate delays or some faults in the circuit. Okay, so there are two types mainly, which is static and dynamic hazard. So suppose that if this was the output. Okay, see, it was supposed to be 0, but it went to 1 and again came to 0, it fluctuated. That's known as static 0 hazard. Similarly, if the output was to be 1 but it went to 0 and came to 1, so that's known as static 1 hazard. And in dynamic hazard, if it had to go to 1 but it fluctuates between 0 and 1 and then it goes to 1, so that fluctuation is nothing but dynamic hazard. Okay, in the next question we have been asked to implement a full subtractor using 3:8 decoder using NAND gates. Okay, by using a decoder and NAND gates. Let's see how to do that. Firstly we will write the truth table for full subtractor, ABC and difference and borrow, and after writing that the next thing is very simple. Note down the min terms here. See, where is difference high here? For this min term 1, 2, 4 and 7. So for 1, 2, 4 and 7 this difference is high, so we will be mentioning that here. Okay, and for borrow also it's the same thing. Now the main thing is you have to make this diagram. You will have the inputs ABC, and from M0 to M7 the outputs will be there, and for difference and borrow, for both you will be using a NAND gate. And see here, this NAND gate connections will be the minterms which you had got here. See, for difference the NAND gate inputs are 1, 2, 4 and 7, right? But the for the input of NAND gate you will have to use M1 dash, M2 dash and M4 dash and M7 dash. That how you will make, that you will be making by using this NAND gate. Okay, since we have to use only NAND gate, we can't use the NOT gate. Okay, so you will be connecting it with NAND gate here, so you will be getting M1 dash here, and that will be connected to here. Similarly for borrow also we will do. Okay, the terms which we need, that will be collecting from here and giving the input to this borrow. Okay, in that we will be implementing this full subtractor. In the next question we have been asked to differentiate between PAL and PLA and then realize the function which they have given using PLA. Okay, so let's see how to do that. In PLA, programmable logic array, you have programmable OR gates, but in PAL you have fixed OR gates. Okay, that's the only difference. Now the function which they have given is these both. Okay, so first we will make the truth table, and then where all these terms are coming in F1, that terms will be making high under F1, and similarly for F2 also that terms will be making high, and then we will make the K map for F1 and write the equation. Similarly for F2 also we will make this and write the equation here. Okay, then for the circuit design we will be writing these two equations here and considering the distinct terms here. See, this is the equation for F1, this is the equation for F2. So the distinct terms are these terms and these terms except these both. Okay, so these all terms you will write here by making a AND gate here. See here, this is the AND gates. Okay, these all terms will be writing there, and these are the inputs A, B, C, D. Okay, and you will connect a NOT gate with each of these, and what you are supposed to do here is, see here, the first term is C D dash. Okay, so C is this one, you will make a cross here, and then D dash, so D dash is here, so you will make a cross here, and this will be connected with this one. Okay, similarly you will do for all these terms, and then see here, F1 has these terms, right? So for these terms you will make a cross mark here. Okay, so for those terms which F1 has, those terms will be marked as X, and then that will be connected to F1. Similarly for F2 also you need to do the same. In the next question we have been asked what is a multiplexer and to implement the following using 8:1 mux. Okay, this is the function which they have given. So let's see how to do that. Firstly, a multiplexer is a group of multiplexer has a group of inputs. Okay, these are the inputs and this is the control input. What it does is this control input selects either this or this for the output. See here, internal diagram of this is this. A is having the control to select either I0 or I1 to this output. Okay, and this can either switch between I1 or I2, either I1 or I0 for the final output. Okay, that's known as a multiplexer. Now to implement this function, firstly we will be making this truth table and marking the y values, and then by using those same as I had previously discussed in map entered variable, we will be writing this table here and comparing each value with D. See here, for 0 0 0 and D is 0, the output is 0 according to the truth table, and for 0 0 0 1 it's 1 here. So when D is 0, this is also 0, when D is 1, this is also 1, so the y will be D. Similarly it's reverse here, when D is 0, this output is 1, when D is 1, this output is 0, so it will be D bar. Okay, in that we will fill all of these values. After writing all of these values, make a note of which minterms have a D here. See, the terms which have D here is this one, this, and so on. Okay, so these terms have the value as D. So these are M0, these are M0, M2, M4 and M5. So you will be writing it here. Similarly you will be doing for D bar and 0 also. So after writing all of these terms, make this diagram. Okay, this is the 8:1 mux. You will have one output and 8 inputs. These are the control inputs A, B, C, and this is the D and D bar. Now for which term it was, see, for M0, M2, M4 and M5 it was D, right? So what you will do, all of these are connected with D. Okay, similarly the terms which had connection with D bar, those will be connected with D bar, and M7 was ground, so it will be connected with ground. So this is the circuit diagram for the given question. Moving on to the next question, we have to design a hexadecimal to ASCII code converter using suitable ROM and give the circuit connection. Okay, so let's see how it is. So the hexadecimal values are from 0 to 9 and then A to F. Okay, these are the hexadecimal values. The equivalent binary values we will be writing here. Okay, after writing that we have to convert each of these value 0, 1, 2, 3, all of these values to ASCII codes. Okay, so for your information, the ASCII code for 0 is 048. Okay, so we will be writing the ASCII value here of 048. Similarly for 1 it is 049, so we will be writing 1 here. Like that till 9 we will do. Okay, till 9 we will do, and after 9 it is A, and the ASCII value for A is 065. Okay, remember these values. For 8 is 065, so we will be writing the binary equivalent of 065 here. Similarly we will be doing till F, and we are ready with this table now. Now we have to construct the circuit diagram. These are the inputs here, W, X, Y, Z. These are the binary values of this hexadecimal. Okay, and in the circuit diagram you will have this W, X, Y, Z, and it's connected to a ROM, and the outputs for the ASCII codes are these. Okay, so see here, the all the outputs are normal, but just here A4 is connected with the NOT of A6. Okay, A4 and A6 are opposite. It's is the NOT of A4. Okay, why it is so? Because see here, this is the A6 and this is the A4. So wherever it is 0 here, it's all 1 here, and wherever it is 1, it's 0. So just for the simplification purpose, we have written here as not of A4, and A5 and A4 are same. See, A5 and A4 both are same here. So we are just shorting it with A5. Okay, and rest all are different. So we'll be taking separate output for each of these. Okay, so this is the circuit diagram for the given question. In the next question, we have to explain the simulation and testing of digital circuits. This is a theory part, but still I will be giving a brief overview of what it is. See, whenever we design a circuit, we have to verify that it's working and it's correct. Okay, so for that simulation is used because it's easier, faster and more economical. Okay, it's to verify it's logically correct and there is no faulty component and the timing is correct, and if there arises some errors, it's due to the possible cases. Okay, so we'll be mentioning that, and it's up to you if you want to draw a circuit diagram, because it's 6 marks question. So you have to draw some circuit diagram also explaining where a fault can occur and how to rectify that. That's up to you. You can use any diagram of your choice and demonstrate it to the examiner. Okay, moving on, we have the next question. Explain the structure of VHDL program, and we have to write the VHDL code for a 4-bit parallel adder. Okay, using full adder as a component. So firstly we will explain the structure of VHDL program, then we will be writing the code for it. Okay, firstly the structure will be as follows: entity architecture. Inside the architecture you will have many modules. Okay, first one is entity part, second is architecture part. Okay, in entity you will be mentioning what are the inputs and outputs, and in the architecture part you will be mentioning what is the equation used for getting the outputs. Okay, so in entity part this is the syntax, this for the inputs, and in architecture part you will have the body. Inside this body you will have the equations. Okay, so let's see how to implement this using a 4-bit adder. See, for 4-bit adder you will have this circuit diagram. Inside this diagram you will have A and B input, C is the carry input, and S is the sum and carry output. Okay, so 3 inputs and 2 outputs. So we will be mentioning that in the entity part A, B are the inputs and C is the input, S and C out is the output. Okay, we are using a bit vector because we are using multiple inputs here and outputs also. Okay, but this carry is just single, right? See here, but this carry is just one here, one input and one output. Inside this architecture we have used a full adder component, so we will be mentioning the inputs as X, Y and C in, and the outputs as C out and sum, and then we have this signal here. See here, this is the input and this is the output. Okay, in between that you have, see here, these 3 carries are present in between input and output, so that is denoted by signal. Okay, so signal C, 3 we have used, 3 carries are used, so 3 down to 1. Then we have to write this begin and end. In between begin and end we have used 4 full adders. So what we are doing is FA0 till FA3, and we will be mentioning the inputs and the outputs here. See, for example, first one A0 B0. A0 and B0 is nothing but this one, A0 and B0, and CI is input, right? So we'll write here CI, and the output is C1 and S0. So we'll write the output as C1 and S0. Similarly we'll do for the remaining 3 also, and after writing that ends the architecture part. In the next question we have to explain the working of SR latch using NOR gates and show how SR latch can be used for switch debouncing. So let's see one by one. This is the design for SR latch, and you have 2 NOR gates here. This is S and R. Okay, now it's very simple here. S means set, R means reset. So whenever you set means you make S as 1, what happens is Q will become 1. Q is the output, so Q will become 1. So when you make R as 1, Q will become 0. R is reset, right? So when you make it as 1, Q will become 0. That's what happens. If S and R both are 0, what was Q, that will remain the same. Okay, so let's see how it works. In case S and R both are 0, okay, see here S is 0 and R is 0. So what will be the inputs for this one? For this circuit Q is 0, right? So here you will get the input as 0 and this is also 0, and 0 0 is getting input in the NOR gate. The output will be 1. That output will be fed to this NOR gate. So here the output is 1 and this one is 0. 1 and 0. 1 and 0, what's the output? It's 0, right? So Q will be 0 here. So it will remain stable as it will not get changed. And in the second case, in case I make S as 1, okay, Q was 0 initially, okay. So when Q was 0, this input is 0. When I make S as 1, okay, so the input is 0 and 1, so the output should be 0. And now this input has 0 and 0, so the output should be 1. So see, Q was 0, it became 1 now. So this 1 will go here and this 1 will be there. 1 and 1, output is 0. So this will be stable in this form. 0 and 0, output is 1, and it will be in the same form. And when we reset it, means when we make R as 1, that time the change will happen. Similarly, see here, when R is 1, the input is 0 and 1, the output will become 0. So when Q was 1, according to R, because of R, this output will become 0, okay, and it will stay stable in this form, okay. And one more thing, if you try to do S and R both as 1, that's not possible, because the circuit can either be on or off. You will understand more when you look at this diagram. See here, this is S and this is R. You just have one switch here. It can be either with on or with off, okay. So you can't have S and R both as 1. Now the debouncing switches means when you on the switch, what happens is this switch won't stay here. It will just bounce for a small amount of time, then it will go and stay here. So due to these bounces, what will happen? Normally the output will become high and low continuously, okay. So when you try to on a light, it will blink for some time and then off, then again come, then off, then finally it will come as on, right? So that's what happens in this debouncing switches. So this can be overcome using this SR latch. Because latch holds the value, what happens is when S is 1, Q is 1, this is the output. So Q will hold the value as on, even if S becomes 0 until R becomes 1. R will not become 1 because the debouncing will not happen till off, okay. So it will just get released and it will go back here. It will not touch this off. So R will not become 1 and S will just become 0 and 1. When S is getting 0 and 1 fluctuations, Q will remain 1 only, because latch will hold the previous value, okay. So Q will not change until R is made high, okay. So Q will remain 1 and that fluctuation can be overcome. In the next question, we have been asked to differentiate between latch and a flip-flop, okay, and show how SR flip-flop can be converted into D flip-flop. So let's see the first one. See, the difference between latch and flip-flop is very simple. Latches are level triggered, means whenever a change happens in the input side, change will be reflected in the output side, okay. But in flip-flop, the change will be reflected only when the clock goes high or low, okay. It's edge triggered. When the clock is rising, the change will happen. When the clock is falling, it will not happen, okay. That's the difference between latches and flip-flop, okay. Then the next question is to convert the SR flip-flop into D flip-flop, okay. So remember, whenever you have to convert flip-flop, firstly you will write the truth table for the desired flip-flop, okay. In this case we want D flip-flop, right? So you will write the truth table for D flip-flop first, then the excitation table of the existing flip-flop, okay, which is SR. So after writing these both, we will merge these both here, okay, D input and SR input. Then we'll make the K map for S and R, okay. See here, we'll make the K map for S and R. Then when we get the equation, and in this case we got the equation as S is equal to D and R is equal to D bar. So we will make the equation here. This SR flip-flop is converted into D flip-flop. How? This D is the input, and according to the equation which we got, S is equal to D, so D will be connected directly with S, and R is equal to D bar, and that will be connected with R. So this is the input and this is the output, okay. So D flip-flop is used in place of SR flip flop. In the next question, we have to derive the characteristic equations for D, T, SR and JK flip flops. For the characteristic equation, first we have to make this table of D and Q. This is the Q and this is D, and what will be the next state when these both are 0 0 0 1 1 0 and 1 1. After noting down this, we have to make the K map and find out the equation, and that's the characteristic equation for D flip flop. Similarly, we will do for the T flip flop and SR as well as for JK flip flop. Okay. In the next question, we have to draw the logic diagram of master slave JK flip flop using NAND gates. This is the same one which we have in lab manual experiment, and explain the working with a suitable timing diagram. Okay. So let's see how to do that. Firstly, make this NAND gates here. Okay, the same diagram which we have in lab manual. After making that, write the truth table, and in this timing diagram you have to demonstrate all of these cases. Okay, when J and K are 1 and 0, 0 1, 0 0, 1 1. Okay, all of these cases you have to demonstrate. Firstly, how to make the timing diagram? First, make the clock signal. Okay, start from here. After making this clock signal, you have to see this. In first case, J is 1 and K is 0, or you can take as 0 0, your wish. Okay, so I have taken as 1 and 0. So in the first, see, consider this as rising edge, and in first rising edge, J should be 1 and K should be 0. So make high, so make J as high and K as low, and when J and K are 1 and 0, what is Q? See here, when J and K are 1 and 0, the Q is this. It becomes 1 no matter if Qn is 0 or 1. So when J and K both are 1 and in this rising edge, Q should become 1. So Q will become 1 here. Similarly, we will demonstrate for all other cases also. That's the timing diagram. In the next question, we have to with an example, we have to explain with an example the syntax of conditional signal assignment in VHDL. Consider this diagram here. In this diagram, you have two multiplexers, and the output depends on the values of D and E. Okay, so see here, in first case, see in this first case, F is equal to A when E is equal to 1. See here, when E is 1, so A will be selected, right? So we will be writing in this way, when select A when E is 1. Else if E is 0, this will be selected, and this output will be depending on C and B. Okay, either C or B can be selected. Okay, so D will be selecting either B or C. So when D is 1, B will be selected, when D is 0, C will be selected. That we are mentioning here, else B when D is 1, else C. So these are the conditional statements which we are using in VHDL. In the next question, we have to write the definition of what's a shift register and explain the working of 8-bit serial in serial out shift register using SR flip flop. Okay, now shift register is nothing but a group of flip flops which have this binary data in it, and that can be shifted either right or left according to the signal which is applied. Okay, so let's see the 8-bit serial in serial out shift register. In this, you will have the 8 bits here. See, this is the compressed form of this diagram here, and then you will have a serial data input, and that will be output here. Okay, so what happens is, when you have some data here initially, when you input some data here, when you input some binary value here, this will get shifted here, and similarly all these bits will be shifted, and this new bit will come in the first place here, and the second and the last bit will get this output from here. Okay, in the next question, we have to draw the state graph, state and transition table and timing diagram for sequential parity checker. Basically, sequential parity checker is used for checking if the data is correct or not. Okay, see, for that what technique we use is, the number of ones should be odd. Okay, total number of ones. In the first row, there is no 1 in the first 7 bits, so the 8th bit will be made 1. Okay, similarly for the second row, we have 1 1 here, so we will be not doing anything because it's odd already. Okay, similarly we have 3 here, and we have 5 here. And similarly we have here two ones, so to make it odd we'll add a 1 here. Okay, so in that way the safety of the data can be ensured. If any changes happen here, this parity bit will get changed, so the change can be reflected. So this is the state graph. If z is 0, z is nothing but the parity bit. If it's 0 here, means see here, S0 is the number of ones received. Okay, even number of ones. If the number of ones are even and z is the parity bit, if the number of ones are even, z will be 0. Z is nothing but this one. Okay, if the number of bits are even here in the first 7 bits, this is z, z will be 0 here. Okay, similarly if S1, if the state is S1 means odd number of ones are there, then in that case z will be 1. Okay, and then x is the input, either 1 or 0 will be the input. Okay, in case if it's 0 input, then it should be S1 only, because it's the odd number of ones received. So if the input is 0, again the number of ones are odd only, so it should remain in this same state. In case if the input received is 1, at that time it should change to S0, because when input received is 1, the number of ones will be even now. See, it was odd, another one was received, so it will become even now, so it will come to this state. And the same thing which is present in this graph is in the form of this table now. Okay, in the next question we have been given to design a T flip-flop whose transition graph is shown in this figure. Okay, for this transition graph you have to design a counter using T flip-flops. Okay, so let's see how to do that. Firstly, we will write the binary values of the given graph, which is 0, 4, 7, 2 and 3. Okay, after writing this, write down all these binary values from 0 to 7, and then see here, after 0 it is 4 here, right? So after 0 0 0 write 1 0 0. Okay, that's the next state. So there is no 1 here, so after 1 there will be no state. Then after 2, see after 2 it is 3 here, so you will write as 0 1 1. Similarly you will fill for all these values. Then after that note down the excitation table for T flip-flop, since we have to create the counter using T flip-flop. So we will note down the excitation table, and then we have to write this present state, next state and flip-flop inputs. See, for the present state and next state, you will copy down these values from the previous table which you have created here. Okay, this will be the same thing, and then you have to fill the values of TC, TB and TA. Now for TC you will consider C and C plus. Okay, according to this, for example 0 and 1. See, for 0 and 1, what's the output? T. So you will so the output is 1 here, so you will write 1 here. Okay, similarly for the next one also you will see these both values and note down the next value. Okay, in that way you will do for B and A also. After noting down these flip-flop inputs, make the truth table for TC, TB and TA, and note down the equation. And after doing that, you have to make the circuit connection. Okay, these are the three flip-flops which are TC, TB and TA, and you'll make the connection accordingly. See here, for the first one, it's TA is C plus B, so it's actually B here. Okay, it's not A, it's B actually. So for TA, what's the input? C or B, right? So C will be connected with C here, and B will be connected with B here. Okay, so this is the input for TA. Similarly you will do for TB and TC according to the equation which you have got here. Okay, and that's the circuit connection. And in the next question we have been asked what's a register, and explain how a 4-bit register with data, load, clear and clock input is constructed using D flip-flops. Okay, so let's see what's a register. A register is nothing but a group of flip-flops and with a common clock input, and they are used to store the binary data. Okay, they are used to store the binary data. And this is the diagram for 4-bit register. Okay, and in this we have load, clear and clock. When the clock is high or rising edge, that time the changes will take place from this one till here. Okay, from the input to the output. The load will enable the loading of these values. Okay, means these values when we enter, if load is 1, that time only these changes will happen. Okay, and this stores the value which we enter here. Okay, that's the working of this register. In the next question, we have been asked to draw a block diagram which explains the working of n bit parallel ladder. Okay, so let's see how to do that. Firstly, we'll write this diagram here, circuit diagram. In this circuit diagram, we have two parts. First one is full adder. As you know, for the full adder, we'll have three inputs and two outputs, x, c and y. These are the inputs, and the output is s and c2. Okay, so when the firstly what we will do, we have to store these values here, means result will be stored here. For that, first suppose that we have to add 3 and 4. Okay, so the binary value of 3 is 0 1 1 and 4 is 1 0 0. See here, 0 1 1, this will be stored in the x part, and next number will be input from here, 1 0 0. So the 1 will come here and this y will come here, and the sum will be stored here. Okay, and this will be accumulated here, and the carry will go here, and the next sum will happen and the carry will go here, and this goes on till the last bit. Okay, so the result will be stored in the accumulator. In the next question, we have to differentiate between Moore and Mealy machines and analyze the following and draw the timing diagram for this circuit. Okay, so let's first see what's the difference between Moore and Mealy machine. Okay, see, the only difference is, in Mealy model what will happen, output depends on the present state and the present inputs. In Moore's model what will happen, the output depends only on the present state, it does not depend on the present input. Okay, that's the main difference. Now coming to the circuit diagram, you have this circuit diagram here, and firstly we will note down the flip-flop inputs for DA and DB. Okay, this is DA and DB, which is A and X, A or X, and X XOR B dash. Then Z is A XOR B. See, this is Z. Okay, this is given to be A XOR B. Okay, after that the next state equations are A plus and B plus. That's nothing but this one, A plus and B plus. So A plus and B plus is nothing but D. Okay, in D flip flop the input will be same as the output. So the input of B is this one, A or X, and the input of A is X XOR B dash. So those two equations, X XOR B dash and X or A, this will be written, and then we'll make the K map for A plus and B plus, and after that the state table is this. Okay, now observe here how we will fill these values. See, A, B and X. Okay, so for A, B and X, 0 0 0, the next state of A is 1 here, and next state of B is 0 here. So 1 and 0 will be written here, 1 and 0 for A plus and B plus. Okay, the next states when X is 0. Similarly for when X is 1, and A, B both are 0, A plus is 0 and B plus is 1. So 0 and 1 will be written here. Okay, in that way it will be filled, and this Z values will be filled according to the equation, which is A XOR B. Okay, so A XOR B will be used to fill the Z values, and the same thing is here. If you consider 0 0 as S0, 0 1 as S1, and so on, so we'll be filling these values also according to this S values. Okay, after doing that we have to make the timing diagram. Firstly we'll start from this clock input. Okay, we'll make this clock signal, and after that the A, B and Z will be filled. Okay, so the number which was given to us in the question is 0 1 1 0 1. Okay, so since the clock is rising edge, at each of this rising edge we will insert one number. Okay, at the input 0 1 1 0 1. At that time the input is X, right? So at this time the X should be low, at this time X should be high. So we'll make the changes in between this. At this time it should be high, so it will remain high here, and the low in this one, and so on. Okay, and the remaining ones are A, B and Z. Initially all these three will be 0, and we will be making changes according to these equations. Okay, for example, see here, the next state of A is X XOR B dash. Okay, initially X is 0, B is 0, so B dash will be 1. What is X XOR 1? X XOR 1 is 1, right? So we will be making A as 1 in the first rising edge. A will become 1. Similarly we will do the changes for B and Z also according to this equation.